In this video, we're going to talk about oscillators. What is an oscillator? An oscillator is basically a circuit that takes in a DC input and converts it into an AC output. Now, the output can be of a sinusoidal nature. You can get a sine wave, also known as a harmonic oscillator, or you could get non-sinusoidal outputs. This would be classified as a relaxation oscillator. You can get the triangle wave. You could also get a square wave. And you can also get the sawtooth wave. An oscillator consists of two main parts: an amplifier and a feedback network. The feedback network in this illustration is indicated by the symbol alpha. Now, the amplifier increases the voltage of the circuit. So let's say this represents the input voltage. This would be the output voltage. The output voltage of the amplifier is equal to the voltage gain times the input voltage. Now, the feedback network is an attenuation network. It reduces the voltage going from the output back into the input. So alpha is the attenuation factor. So as some of the energy goes back to the input, we get a voltage called VF here. VF is equal to the attenuation factor times the output voltage. Now, in order for the circuit to work, the feedback network must provide a signal that is in phase with the input signal. The amplifier provides a 180 degrees phase shift relative to the input signal. You can see that these two waves are 180 degrees apart. Now, the feedback network also provides another phase shift of 180. And so what happens is that it's going to be in phase with the original input signal. And this leads to sustained oscillations. So if we add these two angles, 180 plus 180 equals 360. And so thus VF, the feedback voltage, will be in phase with the input voltage. And so you could see the cycle. Once this circuit is given a trigger pulse, let's say if you connect the power supply to the oscillator, the signal at the output is fed through the feedback, going into the input of the amplifier. It gets amplified, comes back out of the output, and the cycle continues. Now, we need to determine the loop gain of this circuit. So if we replace the output voltage with what it equals here, we'll get that VF is equal to alpha times the voltage gain times the input voltage. So the ratio of the feedback voltage to the input voltage is equal to alpha times AV. It's the product of the attenuation factor and the voltage gain of the amplifier. In order for the oscillator to function properly, two conditions must be met. The first one is known as the Barkhausen criterion. That's when the attenuation factor times the voltage gain is equal to 1. So the loop gain of the oscillator network must equal 1 in order for us to have sustained oscillations. And we already mentioned the other condition, and that is the total phase shift must be 360 degrees in order for positive regenerative feedback to occur. Now let's talk about what would happen if the loop gain is less than 1. If the loop gain is less than 1, oscillations will occur initially, but eventually it's going to die out. And so dampen will occur. Now, what happens if the loop gain is greater than 1? The oscillations will occur initially, but they will get larger and larger. eventually they will reach a ceiling where clip-in will occur, because there's only so much that the DC power supply can support. The oscillations won't continue forever. They will reach a ceiling. And so we'll call this, we'll just say V and negative V. So that's what's going to happen if the loop gain is greater than 1. Now, if it equals 1, sustained oscillations will occur. And so we can get a nice sine wave. But initially, everything must start from 0. So initially, if you want your oscillator to function properly, you need the loop gain to be greater than 1. And the reason for that is to start the oscillations. As the amplitude builds, eventually it will reach its optimal point. At that point, you want the loop gain to be equal to 1. So while the oscillations are growing, the loop gain needs to be greater than 1. But once it reaches its optimal level, then you want it to equal 1. Now, there are two common oscillators that you'll come across. There are others, but these are the most common ones. That is the LC oscillator circuit and the RC oscillator circuit. With the LC oscillator circuit, typically you have an inductor connected in parallel to a capacitor. Now, as energy is applied to this network, the capacitor absorbs the energy. It stores it in its electrostatic field. And then the capacitor releases the energy into the inductor as it discharges to the circuit, and the inductor stores that energy in its expanded magnetic field. When the magnetic field of the inductor collapses, that energy is used to charge the capacitor. So energy is transferred back and forth between the capacitor and the inductor. And thus, this circuit will generate a sine wave as the energy cycles back and forth. The frequency of the oscillations can be calculated using this formula. It's 1 over 2 pi square root LC. So two common LC oscillator circuits include the Colpitts oscillator circuit and also the Hartley oscillator circuit. Now, for those of you who want more information on how to build these circuits, check out the links in the description section below this video, as I'll have more information on those topics, including specific values that you could use to build those circuits. Now, the next type of oscillator that you can create are the RC oscillators. Oscillators that use a capacitor and a resistor in their network. Now, with this type of circuit, the frequency is usually some variation of this formula, 1 over 2 pi RC. Two common examples of the RC oscillator circuit includes the RC phase shift oscillator circuit, that's one of them, the Wine Bridge oscillator circuit, and also the 555 timer. All of these simply use resistors and capacitors to generate the oscillator circuit. In the case of the 555 timer, this circuit can be used to generate a square wave. And the formula for that circuit is 1.44 over RA plus 2RB times C. In either case, the resistors and the capacitors are in the denominator of the formula. As the resistance goes up, the frequency goes down. And as you increase the capacitance of the circuit, the frequency also goes down. Now, you can convert the square wave into a sine wave by introducing an LC network at the output. So if you were to add an inductor and a capacitor to the 555 timer at the output, This is the ground, by the way. As long as the frequency of the square waves matches the frequency of the LC network, using the formula that we talked about, the square wave can be converted into a sine wave. But you need to use the appropriate L and C values in order for this to work. You can also convert a square wave into a triangular wave using an RC network. And of course, you need the appropriate values for that to work as well. So with the 5x5 timer, you can make a square wave, you can make a sine wave, or you can make a triangle wave with that circuit. Now, the two other types of RC oscillators include the Weinbridge oscillator, which uses an RC network and an operational amplifier, and also the RC phase shift oscillator, which uses 3 RC networks and a transistor. You can also use an op-amp for the phase shift oscillator as well. Now with the Weinbridge oscillator, the frequency is 1 over 2 pi RC. For the phase shift oscillator, it's 1 over 2 pi RC times the square root of 2n, where n is the number of RC networks in that circuit. Now there are some other oscillators out there, like the negative resistance oscillator and other examples too, but this will be enough for this video. So if you want more information on the oscillators that I mentioned in this video, check out the links in the description section below. Now, before I end this video, I want to talk about how we could derive the formula of the resonant frequency of an LC network. There's 2 other formulas you need to be familiar with. The inductive reactance of an inductor, represented by the symbol XL, that's equal to 2 pi times F times the inductance of the circuit. So the inductive reactance, you could think of it as resistance to an AC signal. It's basically an impedance that the inductor acts against an AC signal. Just as a resistor may resist a DC signal, inductive reactance resists an AC signal. And as the frequency goes up, the opposition to this AC signal goes up. Next, we have another one, capacitive reactance, which is 1 over 2 pi FC. As the frequency increases, the inductive reactance goes up, but the capacitive reactance goes down. And so there's a point where these two are equal. And when they're equal, that's when the circuit will resonate at a certain frequency. So what we need to do is set the inductive reactance equal to the capacitive reactance. So 2 pi FL is equal to 1 over 2 pi FC. Multiplying both sides by 2 pi FC, these two will cancel, and so on the left we're going to get 2 times 2, which is 4. Pi times pi is squared. F times F, we get F squared, and then LC, which equals 1. And then you want to divide both sides by 4 pi squared LC. And so what we have left over is that F squared is equal to 1 over 4 pi squared LC. Next, take the square root of both sides. The square root of 1 is just 1. The square root of 4 pi squared is 2 pi. And then we're left with the square root of LC. So that's how you can derive the formula for the resonant frequency of an LC network. You need to set the inductive reactance equal to the capacitive reactance.